Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a really nice homemade equation. Now I proudly call this homemade because I think I'm the first one to have thought about this idea. I don't know if I haven't seen this problem anywhere else. I didn't take it from a book or website. Let me know if someone else had the same problem, but it must have been done before my video. Okay, anyways, so we have this interesting expression, and when I first came up with a problem like this, obviously, I can show you how I came up with it. It's pretty easy. You just come up with your z and then just plug it in, get the left hand side, and then right hand side is the result. So it's easy to come up with, but I did not know that it could be easily solved. And then one day the solution dawned on me, and I'm like, okay, I'm gonna do this problem because it's good. I love it. Hopefully you're gonna like it too. All right, great. So we have z to the power absolute value of z equals 2 plus 2 times the square root of 3i. Now, what do you notice about this problem? First of all, the absolute value in the complex sense, right? Is there a real sense? And we have z at the base, absolute value of z at the exponent. So that's quite complicated, don't you think? I mean, as z changes, the base changes, the exponent is going to change. So in other words, we have a complex number to some power, which is a real number, a real power, gives us a complex number. So what is that number, right? Great. You could probably guess and check here, but what if you had a bad, like really, really weird number on the right-hand side? This time, you have a good number. I wanted to make sure that this is kind of easily solvable. Anyways, too many, or whatever, too many sentences, too much talking. Let's get to work. So first of all, one of the things that you can probably think about, and I don't know, my first thought was, why don't we replace z with a plus bi? Okay, good, let's do it. Z equals a plus bi. A lot of times this gives us a good solution, right? I mean, it's worth a try. And of course, we have a plus bi at the base, and who is at the guitar? I mean, the exponent is the absolute value, so that's going to be the square root of a squared plus b squared equals 2 plus 2 root 3i. And then I'm thinking, okay, I'm raising this to power, so I could probably just solve for a plus bi from here by raising both sides to the power 1 over absolute value of z, which is in this case going to be 1 over square root of a squared plus b squared. The problem with this problem is we have variables on both sides, so it's kind of hard to solve. But if you think about it, I could probably turn this into something, right? 2 plus 2 root 3i. Okay, maybe I can use the polar form. Let's try the polar form. What is the polar form? First of all, if you have a number like a plus bi, then it can kind of be written as r times e to the I theta. Or maybe we should call this x plus yi because a plus bi has a different meaning here. So if you have a number like this, you can write it in the polar form. R is the modulus or the absolute value. In this case, it will be, let's call this w, and I'm going to call this absolute value of w, and theta would be the argument of w. Make sense? Okay, great. So we need to find two things. What is the absolute value? What's the argument? What is the absolute value? Absolute value of w is actually easy. It's the square root of a squared plus b squared. So it's going to be 2 squared plus 2 root 3 squared and then square root of that. This is going to be 4 plus 12, and that's going to be 4. Awesome. Now we know the r, and then theta can be found by looking at the tangent. It's tangent y over x, right? Y over x is tangent, actually. Oops, what am I talking about? Y over x is tangent theta, right? And what is y over x in this case? It is 2 root 3 over 2. But you also have to be careful which quadrant you're in. If you're in the second quadrant, you kind of have to adjust because tangent is negative, so on and so forth. Make sense? Always pay attention to the quadrant. Or you can use the cosine and sine. That's another way to approach it, which is safer. Anyways, tangent theta is root 3, and we're in the first quadrant. So that means theta needs to be 60 degrees. At least that will be the principal value, which is the smallest value, right, between 0 and 2 pi. So I got two values. Now I can go ahead and write my number, 2 plus 2 root 3i, as follows. 4 times e to the power I times pi over 3. Of course, I'm using the principal value. You can add multiples of 2 pi to it, so on and so forth. And then I need to raise it to the power 1 over square root of a squared plus b squared. And then this should equal a plus bi. Nice. So here's one thing I'm thinking about. 1 over something usually means the root. And since square root of a squared plus b squared is real, we're talking about some real roots here. Okay? Real valued roots or positive roots. Well, the stuff inside the parentheses is positive. And if I root it, I can do it in a couple different ways. For example, I can square root it, I can cube root it, I can do the 6th root. The thing is, if I want to get something nice, and I'm not even sure if that's going to be a nice result, then I probably want to get an integer or a rational root. So in this case, it happens to be the square root, right? Sort of. It's not justified, it's just a guess, a random guess, right? But we're going to verify this. So at least I kind of have an idea what a and b might look like. And when I take the root, for example, suppose a squared plus b squared is equal to, let's say, 3. This means I'm taking the cube root, and this also means that a squared plus b squared is equal to 9. But when I take the cube root of the right-hand side, the stuff inside the parentheses, I'll be getting the cube root of 4 times e to the power I pi over 9, because I have to divide the argument by 3, right? So in this case, am I going to get two numbers that satisfy this equation? Cosine pi over 9 is like cosine 20. I don't think we can find... Can we find the exact value of cosine 20? I'm not exactly sure. I think you can, but I'm not sure about it. Anyways, that's a different story. But this is my first attempt. It's not complete. Let's go ahead and talk about the second method because it's actually going to be conclusive. Okay? Ready? Now, this is the fun part, and this is why I love this problem. And initially, I had made this problem a slightly bit harder, but then I decided, I think, as a first example of its kind, this should be a little simpler. Okay, here's what I'm thinking. We use this strategy a lot with other problems that involve absolute value, especially problems like this. You know, when you have a problem like z to the 11th power equals z bar, those kinds of questions, multiply both sides by z and use absolute value helps out a lot. Or taking the absolute value on both sides first, right? That's what we're going to do. That is the trick to solving this problem really, really easily. Take a look. Take the absolute value on both sides because, remember, if two complex numbers are equal, like z equals w, this implies that their absolute values are equal because, you know what? We're talking about the same numbers. Come on. That'll work, right? So what do you get on the left-hand side? Well, when there's a power, you can always take it out. In other words, if you have the absolute value of z to the n, by the way, n doesn't have to be an integer, you can always write this as absolute value of z to the power n. How do you prove it? With absolute value properties. Obviously, if you have the absolute value of z sub 1 times z sub 2, this can also be separated. And if you apply this n times, you're going to get that. But what if n is not an integer, so on and so forth? Anyways, that's a long proof, but it works. Trust me on that, okay? So from here we get the following. The absolute value you can put outside, and then this one is going to give you a 4. And beautiful. Let's call this number r. We get r to the r equals 4. As you know, this equation has only one solution because if you think about the graph of x to the power x, starts here and goes like this. This is 1, this is 1, and 4 is going to have a single intersection. Therefore, r equals 2 is going to be the only solution. But guess what? That gives us something beautiful because we know that z to the power r is equal to 2 plus 2 root 3i. And from here you get z squared equals 2 plus 2 root 3i. And that's actually 4 times e to the power I pi over 3. And from here you can find z easily. And there should be two solutions, don't you think? 2 times e to the power I times pi over 6. And to find the second solution, I think you need to add pi to this angle. That's going to give you 7 pi over 6. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.